Welcome to this video. We are going to talk about pressure, and we are going to update the notes, continue with our notes from your handout. We're on page 20 at the bottom where it says pressure. Here's the equation we wrote down for pressure, and then we said the unit of pressure, and I think we were a little hasty about this. The unit of pressure is simply equal to the unit of force divided by the unit of area. And when we're dealing with SI units, right, the official units that we use in IB physics, force is measured in newtons, area would be meters squared, and we call a newton per meter squared a Pascal, PA. So a Pascal is equal to a newton per meter squared. And the way you spell this is Pascal. So let's make sure we've got that in the notes. Furthermore, this is the unit we will be using in problems. I did mention a unit that we have seen from chemistry class, the atmosphere. We won't really be using that unit here in this course. We'll be using the SI unit, pascals. Okay. We're going to next draw a box, because pressure for us is all about gases, ideal gases, and where do you keep gases? You keep them in boxes, right? That's where I keep all of my gases. So you make a line here. When you draw a 3D box, you want this line to be parallel to that line. See how they're parallel? And then you want this line to be parallel to this line, right? And then you want this line and this line to be parallel too. That's how you draw a 3D box. Alright, and let's bring this all the way down. Good. There's my box. And inside we have some molecules. Now, let's see. Some molecules like this, right? And you can draw this just once. I'm going to make a second drawing here that I'll use later. Let's say, okay, so let's think about pressure in the context of this box. If you were to let, your clock run for 1 minute or something, or, 10 seconds, and you were to determine the average force on these walls, right? There's the front wall here that we can see. There's this wall. There's that wall. There's this wall on the bottom. And then there's like this back wall too. Did I get them all? There should be 6. There are 6. If you were to determine the average force on all of the walls together, like the average total force, right? And divide it by the total surface area of those 6 walls, then the average total force and the total surface area would give you the pressure during those 10 seconds, the average pressure. Okay? So that's how we think about pressure of a gas. It's how much force the gas exerts on average and in total, how much force on average all of the molecules exert against the area of the walls. So what are the things that impact pressure? Imagine instead of just a few of these flying around in random directions, imagine we added a lot more. Okay? Very good. We had a lot more. Now, you might think, okay, what are we changing? We're changing how many there are. But the relevant thing here is not just how many atoms there are. That's not the relevant thing. The relevant thing is the density, rho. When you increase the density, as long as you don't change anything else, then you're going to have a lot more little molecules exerting force against the walls. And so then the total force, F, the total average force, would be much higher on average. So the pressure is proportional, directly proportional to the density of the gas. There's another thing you can do to increase the pressure. instead of having these molecules move at a slower or, relatively slower speed, get them going really fast. And they all go in random directions, right? They're all going in different random directions. There's as many, moving along the, there's as many going up as down, as many going left as right, and so forth. All random directions. If you speed them up, then now what are you doing? You're increasing how many collisions occur per second. These things are bouncing around much, much faster, and so they spend a lot more time pushing against the wall, in contact with the wall. They spend more time pressing against the wall. And on average, that raises the force. There's less time when they're traveling between the walls, and more time when they're actually pushing up against the wall. So we have more collisions, and therefore a higher pressure, because a larger total force. So the pressure is also proportional to, you might think just the speed of the molecules, c. You might think, okay, not c, but the average molecular speed, right? Because this one might be going at 2 meters per second, and this one might be at 1, this one might be at 3, and this one might be at 2, and this one might be at 3, and 1, and 2. So you would have to use the average speed, c. C bar. The bar stands for the average, or the mean. Okay. In fact, it's not either of those things. And also, by the way, molecules move much, much faster than like 1 or 2 or 3 meters per second. Here's what pressure ends up being proportional to. The square of the molecular velocity, the average velocity, the square of the molecular velocity, but the average of that squared value. So if you take, 1 and you square it, you get 1. If you take this one, which is 2, and you square it, you get 4. And then this one, which is 3, and you square it, you get 9, right? And you do this for all of them, and then you average all of the squared values together, 4, 1, 9, and so forth. That average value, the average speed squared, is proportional to the pressure. There's another easier way to say this. The pressure, yes, no, that's really the best way. That's the best way. So we have two things that pressure depends on. We see it depends on the density and c squared bar, and here's how we write what that is. That is the average square of, the average molecular speed squared. Make that a little smaller. And when we say molecular speed, we're talking about the speed, the average speed squared of one molecule in the gas. Of one molecule. Pretend that says molecule. Use your imagination, right? So that's what we know about pressure.